Right.
Yeah.
When it goes
It's from the last generation of that being said, that was like 7 years ago. But it's not it's not that
You can't tell me that it's you, but yeah, it was, we used Master Failure. It was, there was another console between the 3DS and the Switch.
Well, there was the Wii U and there was the new 3DS and 3DS, but the 3DS fundamentally like
It was more serious.
the one that runs 3DS games.
Switch.
So the Switch has been around for years.
I really like that. It's been out that long.
I don't know, it came out, I'm pretty sure it came out in 2020. Switch came out, when did it?
We didn't be a friend of Switch. No.
Ours was good.
Well,
Yeah, Marker was $27, almost what I used.
I would say quality keyboard cards. I like.
And that's not even the worst part. You know, it's good for like, releasing games. Everyone can play them. Okay, everyone has to switch, but also the
not standing
hardware that it runs
There was
on
another one.
has not been updated for almost 8 years. And so to get wonderful things like
Oh yeah.
Not much. I love the love to like the streets and
There's cars.
This car, oh, that's shit.
Yeah, but the Vader was in it.
It was like one room with one bed. It was like
I don't know.
chair.
I think that's.
I still remember when they did those movies,
my favorite person would be
people were complaining about the fact that we put it back on cars so you could scratch the cable, scratch the glass if there was no soft felt for
The Spy movie and the murder card.
for this.
That was pretty sick.
Like it's
I love
Yeah, no. A whole new thing, you can't make any runs and all the other games that like solid. That's real time. That's real time. That is what it feels like to play. So it's like this one, so my Nintendo Switch is like your original one too, so it's really worth.
I feel like both is
Yes. It's like
so
I can count all the results. I can count the frames.
Yeah, I guess.
Oh, this lady, right?
Yeah, well, I think you made a partial update
It's cost generator. Oh, yeah. Sorry, yeah.
Nice, thank you.
You were looking great. I didn't send it in a bunch of months.
DreamWorks, man.
All right, so last week of classes, Hope everyone's looking forward to it. So I think the ADC final project seems to be going fairly well as far as I can tell. I saw a couple of working circuits, one in each lab, and then a couple of cases where people were extremely close to being finished. So we'll focus on finishing up those projects during the lab on Thursday. If you think you're going to need extra time, which I'm not sure that anybody does, but if you think that's the case, then if you're in the afternoon lab, you could feel free to come in during the morning lab for part or all of it, as long as there's space available. Likewise, if you're in the morning lab, you can feel free to join the afternoon lab if you need a bit more time. So today, what I want to do is sorry, yeah.
I was just gonna ask if like the lab would be open tomorrow, so if you're able to just go to the lab.
I'm not 100% sure. It depends. There's astronomy labs in there. I don't know if they're still doing makeup labs.
No, we don't have a lab.
No, okay. So yeah, I mean the door could be open. If it's not open, you just have to find somebody to open it. Yeah. Okay, so what I want to do today is I want to just remember what we said about transistors, how they can be used as a switch, how we used them to make an inverter, and we also did the NAND gate. I want to finish off a couple other of the logic gates just to wrap that up, but we'll use most of the time to analyze how the analog to digital converter circuit works. And so those notes will be based off of this diagram. So if you don't have a copy of this, you can come grab one if you need it. Okay, so transistor switch. The basics of what we need to know for our discussion today is the following. If we make the input voltage low, then the current through the transistor is 0. If we make the input voltage high, then the transistor is conducting and we allow current to pass through. So what we were able to do is we were just able to say that, well, since the output is this VCC minus the current through the transistor times RC, when this is low, the current is 0. And so suppose VCC is 5 volts, then we have a high output. On the other hand, if we make this high, the current's non-zero, we get 5 minus some large number, that brings the output to a low state. And that was how it functioned as an inverter. Then what we decided to do is, well, what if we were to put 2 transistors in series? Well, in that case, I need both transistors to be conducting in order to have a non-zero current to ground. And that means that we only get a low output when both inputs are high. Otherwise, the output is always high. And this was the NAND gate. So what are we going to do to make, say, an AND gate? To make an AND gate, what we're going to do is we're going to consider moving the output and the resistor RC. Okay, so what we'll do is we'll start with the same series combination of transistors. So I'm going to have one transistor, which I'll call, say, Q1, and we'll have some base resistor, and we'll have an input that we'll call A. And then I'm going to put that in series with a second transistor, say Q2, and we'll have our second base resistor, and we'll have our second input A. So this is the same sort of configuration that we had for the NAND gate, right? We can look at it right here. For the NAND gate, what we did is we put a resistor and an output above the first transistor, and then below the second transistor, we had a direct connection to ground. So what we're going to do is we're going to do something a bit different this time. I'm going to put my VCC right up to the collector of the first transistor, Q1. this will be connected to ground, but I'm going to connect it to ground through this resistor because it's connected to now the emitter. So this is collector, base, emitter, collector, base, emitter. I'll call the resistor RE. And I'm going to measure my output now. The out is going to be here. But now this output is just determined by the current through this resistor. So I times this resistance is equal to whatever the voltage is at my output. So that the difference is that now the output is not VCC minus a current times resistance. It's just current times resistance. And so we can construct a truth table for this circuit. So what do I want to do? I'll say A, B. We'll write whether the transistors are conducting. And then we'll say the current, and then we'll have the output. Okay, and so we'll try to fill this in. So what we'll do is the possible inputs are always the same. They look like that. And what we know is a transistor is conducting when the base voltage is high. So wherever we see a 1, that transistor would be conducting. So there are no 1s in the first row. There's 1 in the second row, 1 in the third row, and both transistors are conducting in the last row. This part of the truth table is exactly the same as what we had for our NAND gate. It's still true that the only way we're going to have a non-zero current is if we have a path through both transistors. And that only happens once. It's this very last entry in our truth table. And so that's the only one where the current is not equal to 0. Now, in all these cases where the current is 0, the output has to be 0 because it's just current times resistance. And so we get all these low cases. We get a non-zero current only in the last instance. And so we would have a high voltage in that case. So what does this truth table look like? It's not the NAND gate, but it's the AND gate. And so this is the AND truth table. Okay, and so this transistor circuit is equivalent to an AND gate. Okay, so we've done 2 examples where we've put transistors in series. What might you think of doing, if we can combine them in series, how else could we combine them? Yeah, let's give that a shot. So let's try a parallel combination of transistors. Okay, so here's how we're going to do it. We'll have our VCC here. I'm going to go ahead and put our resistor back at the top. I'm going to call that RC, and we'll measure our output just after that resistor. What we're going to have is some current IC, and our output will again be VCC minus IC RC. Okay, so now we've got to place our transistors. What we'll do is we'll put 1 over here. So we'll call this input A. This is maybe transistor Q1. And then we'll go down this. And then we'll place a second transistor over here. Let's see if I can draw this in a reasonable way. Whoops. And we'll have a ground connection here. Here's our second base resistor, and we'll call that input B. And we'll call this Q2. Okay, so what in principle will happen here is if we have a non-zero current, it's going to meet this junction and it'll split. In principle, part of it can go through transistor Q1, so we'll call that I1, and part of it can go through transistor Q2, we'll call that I2. All right, so let's try to do the truth table. All right, so A, B, Q1, Q2, and then we'll have IC, and then we'll have our output. So a lot of this is similar to what we've already done. The input combinations are always the same. Whether a transistor is conducting or not is just determined by whether an input is low or high. So this column is no different than in the previous example. The only difference is now I don't need to go through both transistors in order to have a non-zero current. Because they're in parallel, I could have one of these currents zero and one of them non-zero, and that would still lead to a non-zero current through RC. And so by the junction rule, this IC would have to be equal to I1 plus I2, because when the current into this junction is IC, and then the current out is I1 and I2. Okay, so let's see. If both transistors are not conducting, what's the value of this current? 0, right? That case certainly has to be 0. And if we have 0 current, then we have VCC minus 0, so we have a high output. All right. So now is the current, if I have one transistor off and one on, I could have, for example, Q2 on, so then I have a non-zero I2. Q1 is off, so I1 would be 0. But because IC is I1 plus I2, we have 0 plus a non-zero value, so we have a non-zero current in this case. Non-zero. So then we have VCC minus a voltage drop, which is going to bring the output to low. The next row is exactly the same, except for now it would be I1 that's not 0, and I2 that is 0. We're still going to get a low output. And then when both transistors are conducting, we could have non-zero currents through both of these transistors, and we'll still get a low output. So what is this truth table telling us? The output is high only when both inputs are low. What is that? NOR, that's right. If it was an OR gate, we would have 0, 1, 1, 1. So the inverse of that is the NOR gate. And so this is our NOR gate, which would look something like this. So A, B, and out. I'm not going to do it, but what would you change about this if you wanted to make an OR gate? Yeah, we would take the resistor, we'd put it down here, and we'd measure the output above our resistor. I'll leave it to you to confirm that that does indeed produce the desired OR gate. Okay, good. So what I want to do is I want to talk about the analog to digital converter. And so you all have a copy of this figure. If you don't, they're up here and you can come grab it. This is just a block diagram of the circuit that we've been working on. To this point, what we've done is we've understood the behavior of all of the little subcircuits, the pulse generator, the square wave or clock generator, flip-flop, counter. This is just a little NAND gate. And then we have our ramp generator and our comparator. And so we've analyzed all those little pieces and we want to see how do they all work together. Okay, so what I'm going to do is I'm going to refer to the numbers on these blocks. So 1, 2, 3, 4, 5. Where's 5? Near the center. Oh, it's just a NAND gate, and then 6 instead. Okay, and we're going to construct that timing diagram that I was talking about on the course website for the things that we should see in your lab notebook. All right, so here's the goal. The goal of the analog to digital converter is to output a binary or digital representation of an analog DC voltage. Okay, and that DC voltage is right here. It's the non-inverting input of the comparator. And so we built that last week with the variable resistor. And so I can adjust the value of VDC by adjusting the variable resistor. And I could put it anywhere between 0 and in principle up to like 15 volts, although we're going to use the range only from 0 to 10. All right. So for example, if the VDC voltage is 5.3 volts, we want the output to look like, well, we have 2 counters and they can count 0 to 9. And so we want one of those counters to output a 5, and the binary representation of 5 is, here's the most significant digit, 0, it'd be 1, 0, 1. Okay, so that's our binary representation of 5. And then we'd want the other counter to be outputting a 3. And we can imagine like a little decimal point between these two. So our counter, one of them is going to tell us the voltage in the 1's position. And then the other will tell us the voltage in the 10th position. And 3, binary 3, would be 0, 0, 1, 1. Okay. All right. So how are we going to achieve that? So what we need is the following. We would need 53 clock pulses passed to the counter. And then what we want is once we've counted up to 53, we want to stop those clock pulses. We don't want to count anymore because then we would overcount and we get a voltage, we'd get a reading that's bigger than the actual voltage that we're trying to measure. So once we reach the desired number of counts, we want to block further clock pulses from reaching the counter so that we can read a stable output. Now, we're going to want to introduce a little more flexibility because what we have this variable DC voltage that we can tune. So maybe I start at 5.3 and I read that 53, I count those 53 clock pulses. But then I go and I adjust that voltage. And so now it's 6.7 volts. And I want now to read 67 at my output. So what we're going to incorporate is a signal that will reset our counter. and then allow it to count again. But if the DC voltage increases, we want it to count for a little bit longer so that we reach 67 instead of 53. So that's the objective. So we want to keep this stable output until a reset pulse clears the counter. So then we should initiate, that doesn't look right. Initiate the counting again. Okay, so let's see how this actually works. And what I'm going to do is I'm going to put these little numbers here. Those numbers correspond again to these block diagrams. So number 1 is the pulse generator. And what we're going to assume is that we start just after we've gotten this low to high pulse, which goes and clears the counter. So the counter is going to be reading 0. That's our starting point. Okay, so we assume that the counter was just cleared by a reset pulse. Okay, I'm going to give myself some room. So I'm going to add a page here. Let's see, add a page. Good. All right, and we're going to start plotting some of these curves. So we'll say this is our pulse generator output, and we'll plot it as a function of time. And what we're going to imagine is that we've just had one of these reset pulses. Okay, so that's our starting point, like so. Okay, well, what else happens? If we've just had a reset pulse, then there's another inverter here. So instead of going low to high, after this inverter, it's high and then pulses low. This flip-flop is designed so that the output Q and Q bar are determined by which of the 2 inputs was last to be low. And the way we've done it, S bar was last to be low because we've just received a pulse from the reset. When S is last to low, Q is 1 and Q bar is 0. Okay, so that's the next thing that we can make note of. S bar is high, but was just pulsed low. And what that means is Q is equal to 1, Q bar is equal to 0. All right, so we can add a couple plots here. So we'll have a plot of what's called S bar in that diagram. And it's sitting high, but it was just pulsed low. And so it's sitting something like that. I also plot here the outputs of our flip-flop. So we'll have Q, and after this is pulsed low, Q is going to be high. Okay, so I'm going to say right here, Q has to be sitting high. And I'll leave it like that for now. And Q bar has to be low. Okay, so that's the status of the parts of the circuit that we've looked at so far. All right, so we're going to go to circuit 3, and I believe circuit 3 is the ramp generator, and it is. So we just said Q bar is low. Q bar is also our trigger input. And for our ramp circuit, when the trigger is low, that's when we're actually integrating. We're making the ramp. So we are now generating this ramp. Okay, so since Q bar is equal to 0 or low, the transistor is not conducting. And the ramp generator is producing a ramp. Okay, so we'll draw that. I'm going to extend this dashed line down. Q bar is low, and so we are outputting a ramp. And so I'm going to draw the ramp like so. And we'll add to it a little bit later. So this is the ramp generator. All right. So I assume that 4 will be our comparator circuit. And there it is. So initially, just after the reset has happened, our ramp is just started. So it's starting from 0 and increasing. And so it's some low voltage initially until it has some time to build up. What the comparator does is it compares the ramp to our DC voltage that we're trying to measure. So if our DC voltage is at 5.3 volts, then initially our ramp is below that. And because the DC voltage at the non-inverting input is greater than the ramp at the inverting input, the comparator outputs a high. It'll stay high until our ramp reaches that DC voltage. Okay, so that's fair enough. So we would say initially, the ramp input is less than VDC. And so therefore, the comparator output is high. Okay, fair enough. So we'll add the comparator to our timing diagram. We'll drop this down. And so what we know is that there is a point where this comparator output will just be sitting high, like so. Okay. So I guess I jumped to circuit 6. What is circuit 6 doing? Circuit 6 is the square wave generator. This thing is just producing square waves constantly, okay? So they're just going and producing square waves. That's going to the NAND gate. The NAND gate is going to control when those square waves are passed to the counter and when they're not. But let's just make a note that the square wave generator is just making square waves continuously. So a square wave generator is continuously outputting square waves. Okay, so I guess we can draw that. So T square wave generator. This one never changes. I'm just going to draw a bunch of square waves. It's not necessarily to scale. They would be oscillating probably at a much higher frequency, but this just continues on and on and on and on. Never changes. Okay. Well, we said Q is high, so that's one of our inputs to our NAND gate. Let's say that's input A, all right? I have the truth table for the NAND gate here. And so A is high. And so we are interested in the bottom two rows of this truth table. The square wave generator is feeding input B to our NAND gate. And so it's constantly changing 0, 1, 0, 1, 0, 1, 0, 1. When the square wave is low and the Q is high, we'll get a high output. When the square wave goes high, the output goes low. And so that means if our square waves is constantly switching between up and down, the output of our NAND gate is also constantly switching up and down. And that's going to our counter, the clock input of our counter. And so our counter is actually counting at the moment. And so let's just make a note of all of that. All right, so initially, whoops. We'll say initially, since Q is equal to 1, the NAND gate, which is circuit 5, passes clock pulses to the counter, and the counter is actively counting. So what's happening is the ramp is increasing. While the ramp is increasing, we're passing square waves to the clock input of our counter, and the count is increasing from 0, and we're starting to approach the value that we want, say 53. So what we're going to have to do is, let's look at circuit 4 now. We'll go back to the comparator. Have a ramp that's less than this DC voltage initially, but eventually the ramp reaches that DC voltage. And when that ramp reaches the DC voltage, the output is going to switch from high to low, and that's going to trigger a series of events that is going to help us read a stable output. So 4. So we're back to 4, back to the comparator. Eventually, the ramp output reaches VDC, which causes the comparator output to transition from high to low. All right, so I want to sort of represent some of that in our timing diagram. And in order to do that, what I'm going to have to do is I'm going to have to add VDC to our ramp circuit. So let's suppose that this is our VDC here. So this is VDC. All right, and so I can just continue this. We'll keep that constant the whole time. All right, so there's going to be an important moment here where the ramp reaches this DC voltage. And what did we say? We said the comparator was going to switch from high to low. So at this moment, the comparator goes low. And so I'm just going to draw just a little bit low here. All right. And we have to go look at what happens when the comparator goes low. Okay, so here's the comparator output. It feeds back to the flip-flop. And remember, the flip-flop state, its output, is determined by which of the inputs was last to be low. The reset pulse initially made S bar last low, but now the comparator going from high to low makes R to be last low. And the flip-flop is going to change its outputs. It's going to go from 1, 0 to 0, 1. Let's just look ahead a little bit. If now input A is 0, now we're interested in the top 2 rows of this truth table. The input B is still the square wave generator, and it's still constantly switching 0, 1, but it doesn't matter because the output in either case is a 1. And so this is going to block further clock pulses getting to the counter. And so the counter is going to sit at a stable count after this, after the comparator transitions high to low. Okay, so let's make some comments about that. All right, so come on. All right, so 2. So the low comparator output, which is R bar. Yeah, the comparator output is connected to R bar of the flip-flop, causes the flip-flop to change state. So Q bar goes from 1, 0 initially to 0, 1. Okay, so let's add that to our timing diagram before we go further. So our Q is going to go from high to low, and our Q bar is going to go from low to high. All right. So then I think you want to make a couple of comments about that. So I think I want to. Okay. So now with sorry, I need to look at this circuit one more time. So come on, let's go get rid of that. All right, so now Q is 0, and so that means the output of the NAND gate is always high, and our counter's not counting. Now with Q equal to 0, the output of the NAND gate is always high. Therefore, no clock pulses reach the counter, and its output is stable. Okay, good. So I want to add one more little plot to our timing diagram, and this is going to be the clock input to the counter. And I'm going to extend these dashed lines down. And what we know is during the ramp voltage, which is up here, we are passing clock pulses to the clock input of our counter, and that continues until the comparator changes state, which is indicated by the second dashed line here. After that, the output is stuck at high from our NAND gate, which is also the input to our clock signal. Okay, so what's going to happen now is we've also changed Q bar. Remember, Q bar was also the trigger input to our ramp generator. We're in a state now where Q bar is high. And if Q bar is high, then our ramp generator has this transistor switch, which is conducting. That transistor short circuits, remember, the capacitor, and it has a direct connection output to the inverting input, but that inverting input has to be ground because the non-inverting input is ground. So our output of our ramp goes to 0. Okay, so this is circuit 3. So now with Q bar equal to 1, that makes the transistor conducting such that the ramp generator output is 0. Okay. So our ramp output is going to go to 0. All right, we're getting close to being done. If my ramp is now 0, what's going to happen to the comparator output? We have a DC voltage, which is say 5.3 or whatever it is, and our ramp has been pushed down to 0. So what's the output going to be? It's low or high. Which one is it? High, yeah, that's right. So the DC voltage is in the positive input, and it's greater than the ramp, which is 0 and going into the negative input. And so we have a high output here. That high output goes back to R bar. But remember, the flip-flop changes only when one of the is determined by which of these was last low. So switching the comparator back to high doesn't change the states of the output. The output will only change when one of these, in fact, will only change when S bar is pulse low. Okay, but we should make a note of that. We could say now, since the ramp is 0, since the ramp is 0, the comparator output is high again. Okay, so what that means is that this comparator output, it really goes low for only a very short time. It goes low when the ramp reaches that DC voltage, but as soon as that happens, we end up changing the state of the trigger on the transistor, and the ramp is shut off to 0. And that causes the comparator to go high right away. So the time that the comparator is low is just a very short duration pulse. Okay. And now what's going to happen is all of this will be stable, and it will be stable until we switch the state of the flip-flop. And the state of the flip-flop is only going to be switched when there's a reset pulse. Yeah.
Because the reset pulse is automatic.
Yeah.
You have to adjust the frequency such that it's not just flipping on and off or whatever.
Yeah, that's right. So the time between reset pulses is quite long. It's 0.2 seconds. That doesn't sound long, but in terms of the other things that are happening in the circuit, it's a really long time. And that's intentional because what we're trying to do is we're going to try to let the counter count up and then hold a stable state long enough that our eyes can read it as a stable output. And the square wave generator has I don't know, it's the time between square waves is something like 50 microseconds. So that's much shorter than the 0.2 seconds of the reset. So we purposely make the time between resets long. That's why it had that big 220 microfarad capacitor in place. That was the reason for that. Exactly. Okay, so what we could do is we could say, if we go back now to look at circuit 5 is the NAND gate, and we still are sitting here with Q low, and so no matter what, we're not passing pulses to the counter, the clock input of the counter, and everything is just now stable. So since Q is equal to low, the output of the NAND is always high. Therefore, clock pulses are not passed to counter, and the counter output is stable. So we can extend a lot of these curves because nothing is going to happen until we get a reset pulse. And so let's imagine that we don't get that reset pulse for some time. And so there we go. All of this just remains stable. This remains the case until the next reset pulse arrives, and the entire sequence repeats. Okay, so before I go and draw the entire sequence again, which we will do, what would you do if you found that you got this working analog to digital converter, you set your DC voltage to 5.3 volts, but you're reading maybe you're reading 46 at the output. How would you correct that? Why do we have a variable resistor here in our square wave generator? Yeah.
To adjust the RC.
Yeah, exactly. It's adjusting the frequency or the rate of these square pulses. And so if you have a count that's too low, what you would do is you'd adjust that variable resistor to increase the frequency of your square waves so that you count more of them during the time that the ramp is building up. And so that's the calibration procedure. This variable resistor is for adjusting our DC input. This one is for calibrating the output. So same thing, if you got a count that was too high, then you would adjust the variable resistor so as to decrease the rate of square wave pulses. Okay, so that's the calibration. So let's just finish this diagram off. let's imagine that we get a second reset pulse over here. So there's our next reset pulse. I will extend this down like so. Okay. So that's going to cause S bar to be last low. When S bar is last low, the output of our flip-flop is Q is 1, Q bar is 0. And so Q is going to go to 1, and Q bar is going to go to 0. And what will happen is our ramp will start building up. Our ramp is going to build up just until the point where it touches VDC. Okay. The comparator will stay high until we reach that DC voltage right here. Once we reach that DC voltage, the comparator output will momentarily go low. When it momentarily goes low, that's going to change the state of our flip-flop. And so our flip-flop will switch like so. Okay, I'll fill in some of these earlier things as well. Okay, good. What we will find is that we will pass our square wave pulses to the counter only during this interval when the ramp is making its ramp voltage. And so we're going to pass these square waves to our counter. Our counter is going to count up. Once we have reached, the ramp reaches VDC, we block further square wave pulses and we have a stable output, and we can read it off of the LEDs that are monitoring or displaying the output of the counter. Okay, and then this will continue like so. All right, good. And so that is the operation of the analog to digital converter. And, you know, it's kind of nice. I like this final project because it incorporates a lot of the things that we talked about throughout the term. You know, there's a bit of RC circuitry to get the square wave generator and the pulse generator. There's an op-amp circuit to make the ramp, an integrator. There's a transistor switch to turn the integrator off and on. There is some logic to make the flip-flop and the NAND gates that control when we're counting and when we're not counting. And so it kind of combines a lot of the elements from the entire term into this one pretty nice functioning circuit. And the goal for Thursday will be for everyone to get a working analog to digital converter. All right. Thanks very much, everyone. We'll see you on Wednesday.